Okay, so kind of where we left off, we were talking about the different branches of pharmacology, and we're on number 3. We're talking about pharmacokinetics. Recall that the other branch of pharmacology was pharmacodynamics, which is kind of like, where a drug might interact with its drug target. Pharmacokinetics is kind of the other situation of how the body deals with a drug when it's absorbed. And recall that there's the kind of four sub-branches of pharmacokinetics. So 4 processes. Which we called ADME. And those are absorption, distribution, metabolism, and excretion. And this kind of deals with the chronology of how the molecule enters your body, is distributed to the various drug targets. It's metabolized usually by the liver and then excreted usually through the kidneys or through the colon, so either through urine or feces. All right, and we already talked about absorption and the different types of absorption last time. So different like oral, basically enteral and parenteral. Enteral would be oral generally, parenteral or different non-intestinal processes. We talked about all these IV, intramuscular, subcutaneous, etc. So we got all this from last lecture. Topical, sublingual, transdermal, inhalation, etc. Okay, so let's talk about distribution now. So we're kind of on the second topic, distribution, which is kind of how the drug actually reaches the drug target. And this is usually through general circulation in the blood, and it also involves like plasma proteins, which are proteins in the blood that carry drugs. So how the drug reaches its drug target. And this is so through the blood usually, and in the blood there's plasma proteins which the drug binds to, and this can be a problem if the drug is too tightly bound to the plasma proteins. Because then it doesn't actually release into the drug targets that you're interested in. What other issues? So there's also body fat. So some drugs are stored in the body fat for long periods of time, and we talked about this a little bit. And some of the SSRI drugs like Prozac, they're absorbed into body fat, and also they kind of get stuck in the brain. And so a drug like Prozac will actually last a pretty long time in the body and have its therapeutic effect longer. There's also, what are the other issues in drug distribution? If it's a neurologically active drug, you have to worry about, well, will it cross the blood-brain barrier, BBB, blood-brain barrier? And sometimes that can be challenging for a neurological neurologically active drug, sometimes challenging. Sometimes it's challenging. And I actually have a pretty cool example of this that we'll go into next, all right? So talking about distribution and kind of how drugs reach their drug target. So let's show a cool example of kind of an issue with distribution. Let's check it out. Okay, so an example, that's kind of a classic example that's interesting is the mu opioid agonist fentanyl. Which we talked about before. It's an agonist of the mu opioid receptor. It's a drug of abuse, and people, it's kind of contributing to the opioid epidemic right now. It's about 100 times more potent than morphine. Hundred times more potent than morphine. What was it used for in pharmacology? It's used as an anesthetic. It's used to treat surgical pain and cancer. Terminal cancer, it's used to comfort patients. Interestingly, it has a big side effect, which is constipation. Side effect. Big side effect of constipation. As a drug, it's incredibly controlled due to its abuse potential. It's very, the government is interested in controlling this. And what's interesting is that there's another drug that you could say is a fentanyl analog that's actually over the counter, which seems kind of odd, right? So let's see if I can draw this. Benzene is pH, right? Let's draw it a little smaller. We have two benzenes. A diethylamide. So it's the amide with two methyls, a dimethylamide. It's got the same 6-member ring with the nitrogen on it. It's got an alcohol right there. And it's got a benzene with a chlorine at the 4 position. So this molecule is called loperamide. Loperamide, which is Loperamide. It's also got the generic, actually a trade name for the over-the-counter drug. It's called Imodium. So it's available in the pharmacy, and you think it's actually going to have a lot of the same activity as fentanyl, surprisingly. So it's also an agonist to the mu opioid receptor. It's an agonist to the mu opioid receptor. It is an over-the-counter, OTC. It's an over-the-counter anti-diarrhea drug. It's an over-the-counter anti-diarrhea drug. Even though it's a mu opioid receptor agonist, it is not. It's not a. It's not a. Okay, so loperamide is used as an anti-diarrhea drug, and what it basically does, I mean, if you think about opioids in general, is they have a constipative effect. And when you would have a condition like diarrhea, which has fluidy stool, you would want to kind of reverse that. And by having a drug that has a constipative side effect, essentially that erases diarrhea. And that's kind of how it acts as an anti-diarrhea drug. Okay. The other interesting thing about loperamide is it actually enters the brain. It not only, like you might think it just doesn't cross the blood-brain barrier. It actually does cross the blood-brain barrier. It crosses the BBB. So that must be pretty weird, right? Like how could it cross the blood-brain barrier and be an agonist of the mu opioid receptor and not cause anesthesia or like addictive symptoms? It actually crosses the blood-brain barrier, but there's actually there's crazy. There is a protein called PGP. A protein called PGP, which effluxes it out. It kicks it out of the brain. Efflux protein. Okay, so PGP, and I'll show the X-ray crystal structure in a bit. PGP is a kind of like a drug exporter. So it's present in a lot of parts of the body, and it kicks drugs out of different organs, including the brain. All right. So even though loperamide enters the brain, it gets quickly effluxed out, and that's why it doesn't have this anesthetic effect. And that's why it's an over-the-counter anti-diarrhea drug. Okay. So what's PGP? Let's draw PGP up here. Talk about it a bit. Okay, so PGP is called P-glycoprotein. So P-glycoprotein is an effluxer. It's an efflux protein, and it kicks drugs out of the brain and other organs. It's also called a multi-drug resistance protein. Multi-drug resistance protein. So cancer, a lot of tumor cells actually have PGP, and it is used to kick drugs out of tumor cells, and it causes resistance to cancer drugs. So PGP is kind of like a problem for a lot of drug activity, right? And it's certainly, in the case of loperamide, it's useful to us because we can use loperamide as a anti-diarrhea drug and not have to worry about the sort of the mu opioid receptor and the anesthetic effects. Okay, and it's, yeah, okay. And the other thing, could you add a PGP inhibitor actually to what would happen if you'd add a PGP inhibitor? So if you add a PGP inhibitor, what would be the expected effect? So if you prevent it from being effluxed, you might expect what kind of effect of loperamide? And the answer is you'd actually expect a mild opioid effect, and they observe that. So mild opioid effect. Like a mild, not necessarily anesthesia, but some effects on like the respiratory system, like respiratory depression, things like that are actually observed with these PGP inhibitors. There aren't any super potent PGP inhibitors. And they actually also would probably be toxic, but the PGP inhibitor that people have looked at is called quinidine. And when people have looked at adding quinidine, it causes a mild, it causes some central nervous system effects with loperamide. So that's kind of interesting also. Okay, so we actually have an X-ray crystal structure of PGP, and I'm going to show that on the screen in a second. Cool. Just record it, whatever. Okay, so I ran up to get my computer to show the structure of PGP, which is a cool example of X-ray crystallography, and it's a protein that causes efflux of drug substances. I realized I left my computer at home, so I'm going to have to show that one later. And it's actually on the website too, on the iLearn site. But let's show another example of an opioid that's a similar kind of idea of a drug with anesthetic effect versus a drug that does not have it. And this is for a different reason. All right, so other example. This is the other example, all right? And now we're going to discuss hydrocodone. Hydrocodone, which is also a mu-opioid agonist. It's also a mu-opioid agonist. This you may have experienced at some point if you went to the doctor for like back pain or something like that. It's part of Vicodin. Vicodin is half hydrocodone and half Tylenol. So it has that sort of anesthetic effect of hydrocodone and anti-inflammatory effect of Tylenol. It's not exactly half and half, but it's a mixture of these two things. And anyway, so hydrocodone, as you may know or expect, is a painkiller. So it has anesthetic activity. And as you might expect also, based on fentanyl and the other drugs, it also has constipation effects. Right? And what's the chemical structure of hydrocodone? So all the opioids you kind of draw in a similar fashion. There's a benzene with a methoxy group. 6-member ring on the right, a 5-member ring on the left, and a 6-member ring on the bottom. You have this little CH2 thing popping out and extending out here, and you have a methyl at the bottom, okay? So we have a CH2 right there and a CH2 right there. Okay, so that's the structure of hydrocodone. The methyl is really important, so let's remember that. Nitrogen with a methyl. And you know, you can look up the chemical structure of these things on Wikipedia or something like that. Okay, great. So that's hydrocodone. And what's the other drug? And so the other drug that's kind of related to this is methyl naltrexone versus methyl naltrexone. Methyl naltrexone. And so methyl naltrexone is not an opioid agonist, it's actually an opioid antagonist. Okay, so whatever the agonists do is going to kind of do the opposite. All right, so methyl naltrexone is a mu-opioid antagonist. Okay, what's the, and this drug has no CNS effects. No CNS effects. But since it's an antagonist in terms of sort of digestive effects, you know, loperamide was an anti-diarrhea drug, so that it caused basically constipation, and it was used as a clinical anti-diarrhea drug. Methyl naltrexone is an antagonist, so it's the opposite. It's actually a laxative. Okay. Okay, so what's the structure of naltrexone? You're going to see it's very similar to the structure of hydrocodone. It's with just a couple subtle differences, and that causes its effect as a antagonist. All right, so what's the structure? Start with the benzene and the methoxy. Draw the 6-member ring. Down to the right, and another 6-member ring. Down to the bottom. 5-member ring there. So it looks very similar so far to hydrocodone, yeah, from methyl naltrexone. And just like all of the opioids, oh yeah, the ketone. You got the ketone down there too, on the left. So just like all of the opioids, you have this little bridge now. So you do that by starting to draw a little wedge out there, and then it kind of goes out, over the bottom ring. And now you have a nitrogen down there, just like hydrocodone. But the difference now is this actually has a CH3 and a slightly different group. So it's a methyl cyclopropane. So it's got a you know, that thing. The other difference is it has a OH right here. I think the OH has to do with why it's an antagonist. I think that's a key difference between some of these drugs, is having that hydroxy group there. Okay, so this is methyl naltrexone. What's the charge on nitrogen? It's positive, so that's actually a very critical thing. We've talked about the blood-brain barrier as being sort of a greasy barrier, right? And what do you think happens when you try to pass something with a full ionic charge, a locked quaternary ammonium functional group through the blood-brain barrier? Is that going to work? It does not, and that's why this does not cross the blood-brain barrier. That's why there's no CNS effects, right? Why is it an antagonist instead of an agonist? My guess is the hydroxy group is there, but it's not totally clear with these opioids. Okay, so what's this thing called? What's that thing called? You have a nitrogen with a positive charge. It has a name. What's that functional group called? It's called a quaternary ammonium. There's a quaternary ammonium when you have a nitrogen with a positive charge like that. And that avoids the passage through the blood-brain barrier. That avoids the passage through the blood-brain barrier. Okay, and why does it act as an antagonist? I think it's the hydroxy group. Okay, so then a question might be, what might happen if you take this molecule and get rid of the methyl? Take the molecule and get rid of the methyl. And so a way to draw that in an abbreviated fashion is kind of like this. So we have a couple rings, we have a nitrogen, you have a methyl cyclopropane, it's kind of abbreviated structure. So this molecule is called naltrexone. Okay, so what's the relationship between methyl naltrexone and naltrexone? The relationship is that the naltrexone does not have that methyl there, right? There's no methyl. And so this actually does cross the blood-brain barrier. This does cross the blood-brain barrier, and it is also an opioid antagonist. So unlike that stuff, which did not cross the blood-brain barrier, this it does. And if it crosses the blood-brain barrier and is an opioid antagonist, what kind of therapeutic use might this be used for? And so this is actually used as a, I think I misspelled it, opioid. Opioid antagonist. Okay, so if it is an opioid antagonist, what kind of pharmacological effect is it going to have? It's actually used in like treatment of opioid addiction. Okay, so that makes sense that it kind of counteracts the effect of opioid agonists. So you have this sort of opposite effect. And that is kind of how this works, naltrexone. Okay, cool. And it crosses the blood-brain barrier. One more thought is another molecule that kind of looks like this. But rather than have the methyl cyclopropane thing, what about having an allyl group? The allyl, A-L-L-Y-L, which is that thing where you have a carbon and then an alkene. And this is yet another molecule. This is called naloxone. Naloxone, and naloxone is another opioid antagonist. And it's also, is it a quaternary ammonium? It's not. So this also crosses the blood-brain barrier, and it's used as a opioid. Opioid. It's a hard word to spell. Opioid antagonist. So it's also used as a addiction treatment, drug addiction treatment. Okay, so that's cool how we sort of went from methyl naltrexone, which had the quaternary ammonium, doesn't cross the blood-brain barrier. And then we went to naltrexone, which is just an amine, and it is used as an addiction therapy. And then we went to naloxone, which is the same kind of thing, but has an allyl group instead of a methylcyclopropane. Great. Let's see. I'm trying to see if the blue shows up. Not super well. Okay, cool. That did. Cool. All right, so what comes after phase 2 would be phase 3. So there's another, kind of a third phase in drug metabolism, further reaction. Phase 3. What could that possibly mean? So what that would mean is you do phase 1, which kind of oxidizes or changes the molecule. It's usually oxidation. Phase 2 is attachment of a conjugate. Phase 3 is like further reactions. Further conjugation. Or further reactions. So sometimes the conjugate will get changed or some other kind of thing happens. So that's like what the third phase of metabolism is. Okay, I should say the Wikipedia page for drug metabolism is a pretty good overview and a couple examples of the different phases of metabolism. It's pretty readable. We will go into depth shortly after we kind of finish this broad overview of pharmacology. Okay, if you want to take a look at the Wikipedia page, it's really not that bad. It's actually a pretty reasonable introduction to metabolism. Okay. All right, so the next one, we're still talking about branches of pharmacology. Pharmacokinetics. And let's talk about metabolism now. Which you can define as how drugs are processed biochemically by the body. All right, so there's a couple different mechanisms for how drugs are metabolized. This is also something that we're going to go into great detail later, so I'm not going to go into insane detail right now, but let's introduce this. A couple of the different mechanisms of metabolism are hydrolysis, where things get cleaved, or oxidation. Reduction, oxidation or reduction, okay? These are kind of chemical reactions which sort of just change the structure of a drug. Hydrolysis or oxidation or reduction are called phase 1 metabolism. Phase 1 metabolism. Another type of reaction is called conjugation. Conjugation. And if the initial reactions are phase 1, this is maybe phase 2. So we have phase 1 metabolism, which is kind of initial reactions, and you have phase 2 metabolism. So let's show an example. We're going to go into extreme depth into hydrolysis and the oxidation and reduction reactions and show a lot of examples. Let's just show an example of the conjugation and what I mean by that. Usually when you conjugate something, you're attaching like a polar molecule to a drug that enhances its excretion. Okay? So what's an example of that, where we're going to conjugate something? That's a very common metabolic route. Let's see an example of that. I'll do it up here. I'll just erase this. All right, conjugation. So conjugation. Conjugation. So an example. Is an amine like this. And how could this be conjugated with something in a manner that allows it to be excreted more readily? One of the most common methods for this uses something called glucuronic acid. Glucuronic acid, which I'll have to draw. Glucuronic acid. Glucuronic acid. It's kind of like a sugar derivative. So you start with a 6-member ring, the backwards 6-member ring, and a carboxylic acid right up there. Again, you can Google this also. Glucuronic acid. Then it's decorated with hydroxy groups all around. Okay, so we have the 6-member ring with the oxygen in it, so it's like a sugar, right? With the carboxylic acid up top, hydroxy, hydroxy, hydroxy. Then you have an oxygen, a couple phosphates, and uridine. And what have we learned about these sort of phosphates on biological molecules? They kind of act like a leaving group. So that whole thing kind of gets kicked off as a leaving group. And so in the metabolism process, this phase 2 metabolism, essentially, with the help of an enzyme, this kicks off the leaving group, right? What's your final product? We'll draw our glucuronic acid. Keep the OHs coming. And now this is the drug that's being excreted, right? So this is an example of how attachment of a polar conjugate would enhance the excretion. Because overall, this whole thing is now superpolar. Why is it superpolar? You have all the hydroxy groups, the carboxylic acid. So this is more readily excreted, more excreted. So that's what we call phase 2 metabolism. Phase 1 metabolism we'll get into also. It's also introduction of functional groups into molecules. Okay. All right. So let me erase this. This is the example of phase 2. Okay. Okay. What